algebra. So thank you very much, everyone here, and thank you for attending my talk, and thanks for the organizers for inviting me. I'm an outsider to this community. I'm doing computer algebra, but with categorical flavor, and this means that I have some overlap with some communities, also using categories theory intensively. I was actually puzzled by the invitation because I was starting collaboration with Juan Cuadra, who some of you already know very well. And this was just starting, so I didn't really expect that the organizers already knew this. He's I think he's on Zoom, so you might hear him commenting on some of the stuff that I'm saying. So let me start by mentioning some names. So Sebastian Poser is a former PhD student. He has now some more serious interaction with your community, and he started doing some serious work together with Robert Laubwitz, who should have been here, I think, and some other co-authors. And I mention him all the time because his ideas are floating all over our project. And Kamal Salah is also a former PhD student, and he was responsible for implementing triangulated categories and homotopy categories and derived categories in CAP. Fabian Zegraf somehow overhauled the entire software project and cleaned it up and made it really a bit more future-proof. And the most important thing is he implemented a compiler that you will hear about towards the end of the talk. And Tom Komichel is a current PhD student, and he's responsible for the monoidal stuff that you'll also see here. Yeah, so as I mentioned, when I got the invitation, I was just starting the collaboration with Juan Cuadra, and I gave a similar talk on Thursday last week at the Topos Institute. There I chose a different motivation, so if you want to see a different flavor of this talk, you can just look on YouTube. So now I will start with the motivation that Juan gave me to start interacting with your community, and this was that here. So he gave me this 6-dimensional semi-simple K-algebra of dimension 6, and he asked the following question as for someone who is really a greenhorn and just entering the subject, try to classify all and hop algebra structures over A when the characteristic of K is dividing 6, which is the dimension of the algebra. So here is a software demo, and it took me actually something like 1 or 2 days to write this. And the reason why it went so quickly will be made clear on the next slides. So here is the software demo. So can you see this? Is it big enough, or shall I make it correct? Not big enough. So I have loaded already some stuff, and now I'll define the field F2, 2 elements. And now I want to generate an algebra of generators with relations. So I'll define, because we're working categorically, I'll define a quiver with 1 object and 2 morphisms. These are 2 loops. And now I'll take the path categories. This is just a free monoid on 2 generators. Yeah. And this is the linearization of this monoid. So now the monoid algebra. And this is, of course, infinite dimensional, but not if we take this quotient, the dimension becomes 6. And this is exactly the algebra I just showed you. So now I can view it as an algebra internal to the category of vector spaces. So it's now an object in the category of monoids over this category of row matrices. So we have row matrices and column matrices. It really depends if you understand matrix multiplication as going from left to right or from right to left. Yeah, so this is really, you read the matrix multiplication as the precomposition, as the composition in the way you read Latin from left to right. Okay, and here is the underlying object. So it's really a row module over GF2, so just a vector space of dimension 6. So this object doesn't know anything about the representation anymore. It's just a vector space. And if you display it, it's equipped with a multiplication matrix. So it really forgot about the generators and the relation. And here's the unit. So this is the unit. And I can ask it, is the multiplication then, is it really an internal monoid to the category of vector spaces? And the answer is true. Is it commutative? The answer is false. So we have this matrix block, this 2 by 2 matrix block. Okay. So now let's go back to Juan's question. I'm still not done. So Juan told me actually in characteristic 2, there is a known bialgebra. So he gave it to me. This was this one. So there is probably something I missed. Yeah, to click this line. So this is, you see, it's a bimonoid. So it's a bialgebra structure on A. This is the co-unit, and this is the unit. This is written in a bit clumsy way. This means 1 times x tensor x, and this means 1 times, so this is the scalar multiplication, and this is this element tensorized with that. Okay, so the generators are x and y. Okay, so now I can ask it, is it really a bialgebra? And the answer is true. So this is now a bialgebra internal to vector spaces. Is it commutative? The answer is still no, of course. Is it co-commutative? The answer is yes. So Juan's question was, could you find a non-co-commutative? What did I do? I constructed the affine variety of bimonoids. So this is a variety in dimension 222. So you see here, this is the ring over which I have to define it. And these are unknowns for the co-unit. These are unknowns for the co-multiplications, right? And how many equations do I get? So something like 2,700 and so on equations. So if you plug this in any Grosvenor basis algorithm, I think it will crash. So you need to know a bit how to use Grosvenor basis in order to find points. So I found a point, and it is indeed a bialgebra. It's not commutative because it's still laid on the same basis, same underlying non-commutative algebra I started with, but it's now non-co-commutative. So I could construct for him something that he was happy about. And then he asked the question, could you now find a Hopf algebra structure? So I then went and computed the affine algebra of Hopf monoids. And you see now I need still 36 more variables for the antipode. And now we have almost 2,800 equations. And also you shouldn't solve this just by passing it to Grosvenor basis. Your computer will explode. And what I could show is that this variety is empty. Yeah, but you really need to know a bit more about Grosvenor basis and how to use Grosvenor basis. Okay, so then he told me that he actually knew the answer. He had a theoretical proof that this variety is empty. But then he told me the next question. He doesn't really know the answer, which is in characteristic 3. Okay. So he said he knows a Hopf point, but he doesn't know if this is the only one. And this Hopf point is commutative and is non-commutative, of course, but co-commutative. This was stupid, so let's go here. So this is now over F3. We do the same thing. Now we linearize over F3. You see it here. So now it just is a GF3, and then we internalize again. So this is his Hopf point. And I checked that this is well defined. I computed the variety and I looked at the equations, and then I could prove to him that this is up to isomorphism really the only point inside. Okay. So somehow this proves Kaplansky's fifth in dimension 6 for this thing. And he told me that he doesn't have really a coherent proof in characteristic 3, so it looks as if this is really an advance. So, but of course, maybe some of you know the answer already. So with this motivation, let me switch back. So we had a software which was called HOMALG for homological algebra. So this software was well designed for the intended application, and we didn't have many applications, so it was good enough. The only problem was that at that point, I wouldn't have been able to engage with Juan because the software was not modular enough to cover more applications. And implementing more complicated categories became increasingly difficult. So I already had categories of modules and so on. And then the next step was to implement categories of coherent sheaves. And this was already a pain. But when we really wanted to go on, it really became, you saw the exponential growth in the time and the resources you have to implement. And the remedy of this is already known since, I don't know, several decades. It's called category theory. You have even to organize computer algebra using category theory. And what I mean by this is category theory should guide all design decisions in your software. And categories, functors, and so on should not just be meta stuff that you use to organize, but they should become like natural numbers. You should be able to compute with them, right? And you should actually turn category theory into a programming language. And this means precisely that you should stop writing ad hoc code and you should write your code in categorical vocabulary. So let this maybe sink in. So I want to show you another application that if you take this stuff really seriously, you can even do theorem proving with category theory. So not just these very particular applications. So this is a tower of bi-adjunctions. So they start as two adjunctions, but at some point they become less strict. So they become bi-adjunctions. And this gives you a free model of abelian categories. So in this free model of abelian categories, you can really do theorem proving in abelian categories. So, and you see that there are several several free forgetful adjunctions here. If you start with a quiver, like we did, there's the path category. So this is left adjoint to forget to taking a category and just looking at the underlying quiver. Yeah. The next step you also saw on the previous slide is when you take a path category and linearize it. This is left adjoint to when you forget the linear structure. And then there is a leap on which I will focus on the next slides. And this goes from here and makes the free abelian category of this linear category. Okay. So you can start here with everything, anything, not just one which is a linear closure. So here is a focus. So if you want to go, so here is somewhere K abelian closure. So the first step, what you do is you universally add direct sums. So you have here K linear categories, you have here K additive categories, and there is again a forgetful functor where you just forget the direct sums, but this there is a left adjoint. And what you do here is you add universally co-kernels. This is a construction due to Peter Fried, and it's known since decades. You just need to implement it. So additive closure formally adds direct sums, and you can view it in this way. Additive closure simply invents matrices. If you search for the solution to this problem, to this optimization problem, yeah, as a left adjoint, right adjoint optimization problem, you simply come up with the data structure of matrices, right? So if you would do this for the coproduct co-completion, you will come up with the data structure of functions. So Fried formally adds co-kernels, and it's just a quotient of the arrow category. So you say, I want now to view morphisms, but I want to view morphisms by viewing their co-kernels, right? So you take the arrow category. This means you take as your object your morphisms, but actually you're not interested in the morphism, but actually it's in your co-kernel, and this means that you have to take a quotient of this category.
Is it the same as pre-shift category?
Exactly. So sort of. Yeah. So this here is a pre-sheaf category. This composition.
Yeah, the fried as well.
Yes.
The fried as well.
Yeah, fried as well. Yeah, because you're adding direct sums again, but direct sums of direct sums are direct sums. Exactly. Yes. Very good. So they will come. So the above tower of categorical constructions is typically composed of several free forgetful two adjunctions between a two category D of categories. So this is k-linear categories, for example, and these are the k-additive categories. So between a category of structured category, which we call D for doctrine, and a category of more structured category, E is then for an extra structure. So this is what you've seen on the previous slides. And here are the doctrines that are already implemented in CAP. There's something like 82 doctrines. So you start with the category of quivers is out of this picture. So this is category of categories, or the doctrine of categories. And then you can see here all the way you can go to abelian categories, and this somewhere here you see pre-abelian. At another point, even elementary toposes, they should be here somewhere. And here you see the monoidal stuff and all its. So of course, this doesn't cover all your applications, but we have already some of this stuff that you're interested in. Back to the talk. So the dual category construction, which didn't pop up till now, but this is actually the most important one, and you can still view it as a two adjunction or as a bi-adjunction. This really goes from the dual, the doctrine to the co-dual doctrine. So this means you leave the one morphisms alone in the same direction. The two so you leave you take the opposite of the category. You leave the functors in the same direction, but you op the natural transformations, and then the opposite then becomes a functor in both directions, right? So implementing the opposite requires a lot of meta programming. This is the most sophisticated category we implemented. And why? Because this should be future proof. So this means whenever you implement a doctrine in the future, this category needs to know about it, although it was written prior to everything else, right? So this means the categories or the doctrines that you support in the future, they have to communicate with the opposite category. They have to fulfill some interface specifications. So, and then you can see that you can define the co-fried, which is the formal kernel completion, as the opposite of the fried of the opposite. The finite completion, which is then adding finite limits, is then the opposite of the finite co-completion of the opposite. The finitely presented co-presheaf is the opposite of the finitely presented presheafs of the opposite. And the category of comonoids is the opposite of the category of the opposite. So let me show you this in the software. So it should have clicked here. So this is the category of in which the bi-algebra was living, and you see here it's called the category of bi-monoids. And to see how it's modeled as the category of comonoids of the category of monoids, category of vector spaces. So as you would like to describe it on paper. So here is this thing a bit more elaborate. So again, you start with a field. This is the category of row matrices. So you see that this category knows a lot about itself. So it's abelian, it's rigid closed, it's rigid co-closed, and these 93 algorithms that were implemented primitively gave rise to 513 algorithms that are written in books. So for example, if you have direct sums at kernels, you have pullbacks, right? So the pullback is implemented in CAP generally. Yeah, the pullback is among the 513, and among the 93, you have to implement the kernel, and you have to implement the direct sum. So then you can go and say, I want the bi-algebra of monoids. And you can display it to see in which doctrines it lies. So it's a category with terminal object, and it's still rigid symmetric closed. And you can ask it, how are you modeled? And you see I'm modeled previously as the category of comonoids over the category of monoids. And by the way, you can also do it vice versa. This gives you another computational model, which might be helpful for certain other computations. And the underlying category is really the category of monoids. And if you display this, you see it lies in more doctrines. So it has an initial object and it's Cartesian. So also it has a terminal object and it's symmetric monoidal. And how was this tower built? It's really the opposite of the monoids of the opposite of monoids, right? As on the slides. And now you say, I want to work with infinite dimensional stuff. So I don't want to internalize in the category of finite dimensional vector spaces, but I really want to start with the category of finitely presented algebra. So this is also implemented. And this lies in the doctrine is co-complete category. So you have co-kernels and you have co-products and you have co-equalizers. It's bi-Cartesian, so you have also the direct product. And you have the tensor product, and all these three things are different. The co-product is different from the direct product is different from the co-product, the tensor product. And now you cannot now internalize, but you can say, I'm now taking the comonoids of the finitely presented algebras, and this is still symmetric monoidal in really an algorithmic way. So everything which is there, everything that you would expect, all algorithms in a symmetric monoidal category should be there. All basic constructions. And this is now the category of finitely presented matrix algebras. Yeah, so now you go back to finite dimensionality. And if you display it, it tells you that I was told that I should have co-equalizers, but I am still algorithmically missing this. So now you can ask it, what shall I implement? And it's telling you, please implement the co-equalizer, the projection onto equalizer, and the universal morphism, so that I can tell you that you're algorithmically with co-equalizers. Yeah. So, and still you can do the category of comonoids as the still symmetric monoid, right? So back to the talk. Any questions? So here's an application where, so this you can also see in the Topos Institute Colloquiums talk. I like this example because it's simple and it shows you also that you can use the software to do some sort of theorem proving. So I would like to show you the snake lemma in full generality, a part that will be using Q linear categories over the rationals, not over the integers. And what is the context that you need to teach the computer? So the context is the following. You have three composable morphisms, small a, small b, small c, and subject to the relation that their composite is 0. Okay. And then the lemma goes like this. You can construct the co-kernel of A in any abelian category, in particular in the free abelian category on this context. And now the co-kernel D has a competitor, which is B times C, because also A times, in bracket, B times C is 0. So there is a co-lift along the co-kernel, and you can take its kernel embedding. And dually, you take the kernel of C, and G has a competitor, which is A times B. So there is a lift along the kernel, and from this you take the co-kernel, and the statement is that there is a morphism between the kernel and the co-kernel, and this morphism is essentially unique. And if you express the functoriality of the co-kernel and the functoriality of the kernel, then you would even get a longer, so a 4-term exact sequence. Yeah. Okay. And now you saw on the previous slides that we were able to build these towers of left adjunctions. And now I can show you that with this tower, you can actually prove the snake lemma. See this? So I start with the setup that we have on the previous slide. So here, the setup is A, B, C. This is the generating quiver, subject relation A times B times C equals 0. Yeah. So here's the quiver. Now I take the first left adjoint, which is the free category or the path category. Am I right? Yes. And now I display phi. So this is a category which is finite, but in which you can decide lifts and co-lifts, and it's equipped with so-called home structures, something like external home. Those are not them. Now I linearize it over Q. So I define the field, I linearize, I take the quotient. So now A times B times C is equal to 0. So display L. Now I have a linear category, and it's still equipped with a home structure in which I can decide lifts and co-lifts. And now I do this magic. I take the abelian closure as fried of co-fried of the additive closure. You remember co-fried was the opposite of the fried of the opposite. And now I display A, and A tells me I'm actually in abelian category even with enough projectives, right? So the underlying category of A is this linear category. So what is the modeling of A? It's really modeled as the fried of the co-fried, and the underlying category of the fried is this co-fried, and this co-fried is modeled as you saw as the opposite of the fried of the opposite. So now I do the ultimate UNIDA embedding. I take the objects in my quiver and embed them in the category A. So now A, B, and C are now morphisms in the abelian closure. And there I test that in this free model, their composition is 0. And this is true. And now I do what I just did on the slides, yeah? Verbatim, right? I take the co-kernel projection of A. Then I take the co-kernel lift. And then I take the kernel embedding. And then I take the, again, the kernel embedding of C. And then I take the kernel lift. And then I take the co-kernel projection. And now I have my setup. And now I would like to do a chase. And a chase means what? A chase means that you have to go downstream at some point, but you have to go upstream some other point, downstream, upstream, downstream, and so on. So how would you go upstream? Well, the morphism simply has no inverse. So one trick you could do is you could say, like with functions and relations, right? A function is a special relation, and the relation has the huge advantage that I can formally invert it, right? I can flip the relation. So what I do here, I go to a higher category that does exactly this. So it equips the category, every abelian category, with linear relations, right? So now my morphisms are special cases of these bigger morphisms, or these linear morphisms, or linear coarse fluminences. So I view my F as a generalized morphism. Yeah. By the way, this was what I'm telling you here was even though to Gauss in the context of finite groups. It's called even the Gauss lemma. Why this data structure that I'm using is really equivalent to taking a sub-object of the direct product of two groups. So now we view F, D, B, G, and I as linear relations. And now, after doing that, we do exactly what I told you. We just take them in this way. We take F downstream, B is upstream, so pseudo inverse. B downstream, G upstream, I downstream, right? And the whole business of diagram chasing is the statement that this journey is an honest morphism. So it lives in the underlying abelian category. And this now takes something like 20 seconds. And this is also part of the demonstration because this tower is not compiled. Yeah. So 10 more seconds. Maybe you have some question.
These generalized morphisms. Oh, nice. That's true.
Yeah.
Are these generalized morphisms implemented as like
Span
functor in some direction?
no, there the model is you want to have a generalized morphism between two objects in an abelian category. So here you descend to a sub-object. So you take a mono, and here you go to a quotient object. So here you take an AP, and then you take a morphism between this sub-object and this factor object. And these three morphisms are not composable because they look exactly in the wrong direction. You cannot compose any of them. But you can also, because of the Gorsal lemma, you can view this as a sub-object of a direct sum B or source direct sum target. Yeah, and then you can model this as a quotient of the category of spans or a quotient of the category of co-spans.
Okay, so you are modeling it as a category.
Yeah. This is a category. Yeah, you want to see that?
Oh, no, I believe you. I was just wondering if it was extra structure you were equipping it with.
It is a
or you were
category.
actually doing it as a
Category with an embedding.
Right. That's what I was asking.
So now I can extract the honest representative. Oh, I thought it will take some seconds, but this went easily. So now I can check the exactness. So I can take J, H, the homology at this point. So it's HK. The homology at the kernel. So, and the is0 is yes. And now I take the functoriality of the no, this was the functoriality of the co-kernel. No, I'm sorry. Now I take the functoriality of the co-kernel, right? And the homology object, and is0HC is again true. Okay. So there is something even funnier. Because I have this home structure that I showed you, I could just get this object, the source of f, with co-kernel of I, the range of I, so the co-kernel of H, and just ask the system, how many morphisms do I have from the cell here? So imagine I would like to go in this direction. So able to copy. So imagine I would like to go backwards from the co-kernel to the kernel. Yeah, there might be something universal missing that we didn't know about. Remember, this is a free model, so every computation we're doing is a proof, right? So, and he's telling me there is no morphism, so only the zero map. Okay. But in this direction, I get exactly one. You see here, there is a list open, and then there is this thing, and it ends here. So there's only one basis vector. And I can check that this guy is exactly the snake that I constructed by going downstream, upstream, downstream, upstream. So I didn't even need to invent generalized morphisms. So let me show you a tower which is compiled so that you see the difference in this in the runtime. So this is again literally the same thing, but I'm now taking a compiled tower, and you will see the difference here. So now the abelian closure. This is a black box. So the other one was abelian closure as fried of co-fried of additive blah. But this guy is, this is a fried of finite completion. And when you ask what is the finite completion, it's the co-presheaves. And when you ask what is the co-presheaves, it's the opposite of the functor category. And if you ask what is the functor category, it's the presheaf of the opposite. So for us, the presheaf is the main construction and not the functor category, because this makes life simpler. You see this when you program. Yeah, don't go for the functor category, go for the presheaf category. This is the more natural construction. And now you do exactly the same. So now you embed the three morphisms, A, B, and Z, and then you do the construction I showed you before. and then you do the snake. And now I would like to show you. So this is the precomposition, and this took 20 seconds in the previous one. And now you see a small hiccup because not the entire tower is compiled, but part of the tower is compiled. So there is still half a second or a quarter of a second as a hiccup, but the rest goes exactly the same. So you can, it's another model, but it simply works. Right? So to the talk. We still have 10 minutes, right?
15.
15, very good.
Ask a question.
Yeah,
Where, so we said that you work in sort of the three rational category. Yeah. Why? Where does this, how?
because for the second model, the one which is fast, which is compiled, I only can use fields. But for the first one, I could have used the integers. It was not compiled. And then it would have taken even longer because it's not the Gaussian algorithm, which is computing, but the Hermite normal form. Right?
Can I ask another question then? So when you made a check that it's an honest morphism, then how is that implemented? Does it try to guess commuting squares and sort of searches until it can answer the question? Or
No, it tries really to compute a lift. And the computation of a lift is a sort of really solving a linear equation.
okay,
And this, in this case, the linear equation was an equation over Q. But you see, I have to compile the tower. I don't even know exactly the details because I implemented this thing as a tower. So if you're interested in how it looks like, then it also will be interesting for me because I don't know exactly what he finally did at the end. I just know every step, what he's doing in every step, right?
thank you.
Next question. So I showed you this. And along the same lines, you can treat spectral sequences of bicomplexes. So now this could be your input quiver, right? And the relations would be something like you want that this is a complex, so you want that these compositions are 0, that these compositions are 0, that these squares anti-commute, and you can write all this down. And then you can take the vertical homology, and out of the outcome, you can take the horizontal homology. And I think in this case, this is a cohomological spectral sequence, so I have to say cohomology. So you have to take the horizontal cohomology, and then you ask the system, give me a morphism from here to here. And it simply gives you the general morphism on the second page. And you can iterate if you like, but then you have to make your thing wider. And what I did not tell you, which you could also find in another talk at the Topos Institute, is that because we are really constructing these units and co-units of the left forgetful, so the left-right adjunction, these three forgetful adjunction, we can use the co-unit really to extract an algorithm. So we can construct this guy in the free model and then push it through the co-unit and we get code. And this code is written in terms of the abelian category. Right? So I don't even need to think how to implement the stuff. I go to the free abelian category, ask him, give me the witness, push the witness through the co-unit, and I get code written exactly in the language of category theory. Just using kernels, kernel lifts, co-kernels, direct sums, and so on. So there is more computer stuff in category theory that it was also amazing for me to see all that.
You tried this an interesting, like somehow, like really huge explicit differentials in spectral sequences, even if you know exactly where the spectral sequence comes from.
Yeah, because the use of the word compute in theory is not compute. It's just argue by.
Exactly. And have you, like, other examples where it's sort of classically on paper
Yeah,
tricky, and here the program just like runs through the algorithm and tells
Exactly.
you, oh, this is that and that map between the groups CN and CM, or
this was the motivation on the talk I gave on Thursday, because I really went through a spectral sequence to solve a PDE system. So, but this was in the old software. And so we organized the old software in a way that we have abelian categories and spectral sequences and complexes of them. But the problem is with the old software, I wouldn't have been able to help Juan because it was not modular. Okay, so now everything is much more modular and reusable. And the modularity is a point that I'll emphasize till the end of this talk. So you'll see this coming up and up. So yes, we started with something very concrete. I even didn't have a model for the free abelian category. Were not able to do theorem proving at that point, but we were able to compute in abelian categories of finitely presented modules over non-commutative rings. In this case, then the Weyl algebra, because of differential equations. Yeah, and the Grobner bases were the non-commutative Grobner bases, and everything pushed through. And we over-optimized the previous software. But as you know, that the source of all evil is premature optimization. This is a proverb of Donald Knuth, and this is true. We really felt it. We over-optimized the software, and we should have done the optimization at the end. And this is the end of my story here, that the compiler is where you do the optimization and not in your software. You should write the software really like in the book, verbatim. And everything more, the math, the intelligence, everything else has to go elsewhere, right? You just write down the very generic stuff so that everyone can read it. You can also read it after 10 years, right? And do the optimization elsewhere. So we can model different things. So this is then C is you take a data structure outside of the categorical organization, for example, a ring, and then you view it as a category on one object. In this case, a linear category over its field of coefficients or its ring of coefficients. So C of R is taking something outside, which lives in your computer algebra system, and putting it inside your algorithmic category theory system. So if you take a ring and make it into a linear category and take the additive closure, you have a model of the left R modules of finite rank. If you just op it, you have a model for the free right modules of finite rank. If you take the fried, so if you universally add co-kernels, you have a model for the finitely presented left R modules. This guy is only abelian if R is left coherent, and this guy is only abelian if R is right coherent. But you can also do other stuff. So you remember the functor category that popped up, you can apply it to the path category of this quiver. And when you go to finite sets or skeletal finite sets, you get a model for quivers. So on the computer, you have already a very nice model for quivers, which is an elementary topos. And then you can use it to model various categories of diagrams. The one that we started with is the category of ZX diagrams, which is interesting for quantum computing. But we should take the quotient, so divide by the ZX rules. This is something we didn't do because it wasn't part of the proposal. And doing this means that we have to do rewriting. And how do we do rewriting? Using category theory, right? So there is an entire community called the rewriting community, and they ended up understanding all this, and they do everything now using category theory. So, but you can do more. This is what you saw, the free abelian category for theorem proving, the linear representation of groups. And now that you saw that I'm solving Grobner basis stuff and so on, so I need to work with varieties. So I need to work with the opposite of radical ideals. And how do I model radical ideals? I take the ring, this ring and the horribly many indeterminates. I view it as a category. I take the additive closure. I take the slice over the tensor unit, and then I squash all parallel morphisms into one. So this is the ring. This is the ring as a category. These are the free modules. This slice over the tensor unit, these are the ideals with generators. These are the ideals where you forget the generators. And these are the radical ideals. You see really how category theory is so expressive and so nice, right? Yeah, you know what the tensor product here is in this slice of this? The tensor product is the ideal multiplication. And the co-product is the ideal sum, and the direct product is the ideal intersection. So it's really nice. and everything comes out. You don't need to do any of this. Yeah.
So when you post-settleize, like somehow
Equating all parallel morphisms
you
to.
don't want to equate the zero morphism to everything.
There is no zero morphism anymore because I'm in the slice.
So your slice is just injections.
No, but I'm slicing over the tensor unit, so the ring itself. And up there, the zero morphism only comes between. It has to commute, right?
Saying that sort of like, for instance, if the slice map was zero, then
Yeah, exactly. Yeah, but you know, so this category is additive. This slice is not additive anymore. There is no zero anymore. No zero object, no zero morphism. So what are the advantages of doing things in this way? First of all, reusability. So have a look at what you did. So you see, how often do I use the direct sum? Right? How often do I use the op, the most important construction in all of this, right? How often did I use fried? How often did I use func? How often did I use slice? So building blocks can appear in multiple different contexts. And what you saw at the beginning was the monoids of the comonoids, so they're not even on this slide. So the second thing is separation of concerns. Focus on a single concept at a time. So I just implement fried. Yeah, I just implement pre-sheaves. I just implement additive closure. And this means that we can actually, with a very simple-minded theorem prover written in CAP, we can verify our implementation, right? So, and the nice thing is this emergence, and I don't like this word, but I like it only when it's substantiated. I really want to see not just, you know, voodoo, but in this sense, you see that none of these here really knows about this interpretation. So the computational context they were giving rise to, right? And this is really, for me, emergence, that the whole is more than the sum of its parts. Okay. So this, of course, makes development very efficient, and this was the nightmare we had before. You could optimize and over-optimize, and then some guys comes and tells you, could you do this and that? And then you say, in principle, yes, but I still need 2 years to figure out how to answer your question. The only problem with this is now the inefficient execution, which you saw, right, due to the computational overhead. And the solution is you need to compile, right? So this is the optimization that was prematurely done in the previous software project. So this is something that is ABC compilers. So what do compilers do? When you stack data structures above each other and you want to compute, they have to deconstruct, do something, construct to figure out, oh, for the next computation, I have to deconstruct again and then do something trivial and then construct again. This is called unboxing, boxing, no, unboxing, computing, boxing, immediately unboxing, computing, unboxing. And what a compiler does is it simply removes these bumps, the middle ground. And this is why the system was taking 20 seconds to do completely trivial stuff. Okay. So this is what every compiler should do, right? Yeah, this was the, I will tell you more about the compiler. So this is the ABC of the compiler, and this was for the celebration of Fabian's thesis that now that we're taking categorical towers to this end, they're now really becoming useful. And this is the German highway, by the way. So the signs mean unlimited, right? So yeah, just let me dwell something here. So the compiler is doing the standard stuff that every compiler is doing, but it's now in your hands, right? So you can look at the code and you see he's doing something that, you know, there is a categorical theorem to shortcut it, and you can teach the compiler this categorical shortcut. So while he is deconstructing, he is still in the categorical tower. So now he goes from generalized morphisms to abelian categories. Yeah, and now you see, oh, this universal morphism into direct sum composed with the universal morphism from direct sum is just this times this plus this times that. And you can really start teaching the compiler category theory, right? And when you've exhausted your category theory and end up with the basic data structure, you see that he is taking the sum over 1 plus q squared plus q cubed, and you see, oh, this is the geometric series, right? So you can teach the compiler even low-level math, and this does happen. So I'm mentioning this example because I saw it in the implementation of the category of skeletal fin sets. Yeah. So here are timings. So I don't do timings to, I'll say something at the end. So the timings doesn't mean that we're 2 times faster than other people. It's really about computability or not computability. So this is a series of example, and this is the size of the problem. Think about that this is the dimension of the matrix. Yeah. So we have a parametrized series of example, and the one is just the size of the matrix. And the original code here is 5 times slower than the compiled code. And then in 2 dimension, it's 50 times faster when you compile, and then 250 times faster, and then 1,000 times faster, and then 5,000 times faster. And then there is no comparison anymore. And then there is no comparison anymore. And then you're still on the seconds level, right? Yeah. So these are the benchmarks I like. Yeah. Not factor 1.2. So this is for me premature optimization, right? Okay, it still goes on. So we see the difference between finishes in seconds and will never finish. So the compiler can also be used to for removing additional sources of overhead. You see a lot of crap code inside when you really look at what's happening. And for generating categorical code that I didn't tell you about, and as a simple-minded proof assistant for verifying categorical implementation, which I just mentioned on passing. So this is my conclusion. Algorithmic category theory is a high-level programming language. If you take it seriously, using this language for building categorical towers allows to reach a wide range of advanced and complex applications, allowing the reusability, the separation of concerns, the verifiability, and the emergence in a substantiated way. And this approach naturally comes with a computational overhead, as expected, because it's so elegant. And compiler for CAP can avoid this overhead and allowing us to make full use of categorical towers. Thank you very much.
I guess someone asked to ask the question whether you have implemented